Following Einstein in search of a deeper explanation for tunneling.
Science Makes Me Smile, presented by young Dr. JGC, a creation of old Dr. JGC.
I am young Dr. JGC. Let's begin. What if tunneling was classical after all? Quantum tunneling is one of the central concepts of modern physics. It describes the ability of a quantum particle to be found beyond an energy barrier, even when, according to classical mechanics, it lacks the energy required to cross it. In the standard quantum view, particles are represented by wave functions rather than localized objects with definite trajectories. Because a wave function extends into classically forbidden regions, there exists a non-zero probability that a particle may appear beyond the barrier. This phenomenon is known as tunneling. One of the strongest arguments for tunneling comes from radioactive alpha decay. An alpha particle, consisting of 2 protons and 2 neutrons, is confined within a heavy nucleus by the strong nuclear force while simultaneously experiencing Coulomb repulsion from the positive charge of the remaining nucleus. The attractive strong nuclear force confines the alpha particle, while Coulomb repulsion continuously pushes it toward escape, reducing its confinement. Measurements show that emitted alpha particles often possess less energy than would be required to overcome this barrier classically. According to quantum theory, alpha decay occurs because the alpha particle tunnels through the barrier rather than passing over it. The theory successfully predicts observed decay rates and explains why some isotopes decay rapidly while others survive for billions of years. While acknowledging the predictive success of this model, I remain open to the possibility that tunneling is not the final explanation. My concern is not with the observations, but with the interpretation that a particle can simply appear beyond a barrier without a deeper causal mechanism.
Alternative to quantum tunneling, fluctuating energy barrier.
Given enough time and enough internal interactions, it is conceivable that the barrier itself could be altered, weakened, or locally modified by processes currently treated statistically. Escape would remain rare, but it would result from a gradual deterministic evolution rather than a fundamentally probabilistic event. A related possibility concerns the localization of the alpha particle. If alpha clustering occurs preferentially near the nuclear surface, the particle would face a thinner and potentially lower barrier than one formed deeper inside the nucleus. Under such conditions, rare escape events might occur when several favorable factors coincide. The alpha particle happens to be localized near the nuclear surface, its energy is temporarily near a maximum, and the surrounding barrier is simultaneously near a minimum. Individually, none of these conditions may be sufficient to permit escape, but together they could create brief windows in which emission becomes possible. Another reason for questioning whether tunneling is the final explanation concerns the role of the barrier itself. If a particle can pass through a barrier without possessing the energy required to overcome it, one may ask what significance the barrier height ultimately retains. In everyday experience, barriers matter because greater barriers require greater effort to surmount. If, however, passage occurs through rather than over the barrier, the distinction between low and high barriers appears less intuitive. Supporters of the probabilistic interpretation object that if radioactive decay were governed by an internal clock or maturation process, identical nuclei should decay at roughly the same time. Instead, some decay almost immediately, while others survive for years, centuries, or billions of years. This broad distribution of decay times is therefore taken as evidence that decay is fundamentally probabilistic. This objection is compelling only if all nuclei are truly identical throughout their existence. This possibility becomes particularly interesting in radioactive decay chains. If nucleus A decays into nucleus B and nucleus B later decays into nucleus C, then the B nuclei are not all created simultaneously. Some are born earlier and some later, creating distinct age cohorts. Standard theory assumes that once two B nuclei occupy the same quantum state, they are completely equivalent regardless of their history. Yet it is reasonable to ask whether the process that created them leaves subtle traces that influence their future behavior. The decay event itself is highly energetic. Daughter nuclei are often produced in excited states and subsequently emit gamma radiation as they relax. Current nuclear theory assumes that after this relaxation, the nucleus retains no memory of its formation. However, it is conceivable that the decay process leaves behind hidden structural differences not captured by present descriptions. If such effects exist, nuclei that appear identical could nevertheless possess different internal histories. From this perspective, the observed half-life of a radioactive isotope may not necessarily imply fundamental randomness. Instead, it could represent the average behavior of nuclei undergoing hidden deterministic processes. The exponential decay law would then be a statistical summary of underlying mechanisms, rather than evidence that decay itself is intrinsically probabilistic.
Now you see how an alternative classical tunneling mechanism could explain the crossing of prohibitive energy barriers. Fascinating, isn't it?
Thank you for watching Science Makes Me Smile. Remember to like and share with a friend.
Please let us know your thoughts about this episode.